Okay, so the first thing is we have the next test coming up a week from Thursday. Yeah. So exam, what would it be, 3? Is Thursday, November 3rd, is that? By the end of Thursday's class, I'll be able to tell you what topics that's going to go up to. I'm sort of hoping we can get through structures, but we'll see. And there's a quiz at the end of today's class. So now, exam 2, overall the scores were, like the average was fairly good, but it was, there was a pretty strong split, you know what I mean? You know, the concern there is that a lot of people in the class, you don't want to be in the point where the topics start to leave you behind. And so I think your score on this test should be, you know, a strong indication of how you feel your current approach is going. And if this test didn't go well, you know, you might want to make an appointment to come talk to me or come to office hours and talk to me about a strategy for getting back on track, because you got to do it now, you know. It's not a, you know, a lot of times students come and talk to me about like what grade can I get in this class, you know. They'll, like, later than this, like say late November or whatever, they'll come talk to me, what grade can I still get in this class, you know. And the answer then, the same as now, is mathematically you can still do really well in this class, because you can replace one of your exam scores with your final score. There's still a lot of points to be determined, but the issue isn't the points. The issue is understanding the topics, you know. And if you're just starting to get concerned about your grade in the class in late November, that's the real problem, not the points, you know what I mean? So anyways, it's earlier than that, but you got to, if there's a problem, you got to fix it now. Any questions about problems on the test? Okay. Well, if you have any questions about how it was scored, or, you know, you think I took off too many points for this or that or whatever, try to come talk to me in the next week about it. And if you have any questions about the test, I'd be happy to answer them one-on-one in office hours or whatever. Okay, so the next topic we're getting into. Yeah.
For the homework,
Mm-hmm.
why we just have the Centroid
Yeah.
homework, and that is going to be due,
It must be, oh, this Thursday. Yep. Yeah.
And then, if you have questions about the homework, can I ask you?
Yeah, sure. Okay.
It's about Centroid. Can you go over what about the Centroid? Okay, so my problem is, like, I want to capture all the information. Like, I want to get all the x-axis, y-axis. I want to calculate the Centroid, and then I want to use it explicitly in my free body diagram. But in our example, it looks like you don't care about the y-axis.
So in these, where if you have a problem where you need to calculate the centroid of a rigid body, so that you can use it in like a rigid body statics problem. So say you have something like this. To do that problem, you have to figure out where to apply the weight force, and that requires calculating where the centroid is. But say the centroid is, say the centroid for this is here. Okay. The weight force is straight down, which means you can apply that weight force anywhere along the line of action. And if your coordinate system has x horizontal and y vertical, that means that the y position doesn't matter at all. You can set that equal to 0 or whatever you want. It's not going to affect the problem.
That's always true for weight.
It's always true for any force that you can move the point where it acts anywhere along its line of action. So for the weight, if the y-axis is vertical, which isn't always true, but if it is, then the y component never matters. Because, you know, you could move this force if you want. You could apply it here. That, you know, I'm not sure why you would do that, but if you did that, you'd get the exact same answer as putting it at the centroid.
So if we have a distributed
Mhm.
load on top, sorry.
Okay.
And it had like a center of axis that was, or a line of axis that was horizontal.
So
Yeah, that's what you're looking at.
okay, so this one, you have a weight force. Over here, you have the force at the pin joint. You have a cable force there. That triangular distributed load, you know, the centroid of this thing is here somewhere, right? But the force that we're going to apply at the centroid is vertical, and so you can move it anywhere along its line of action, just like the weight force. And so you end up not caring about the vertical position of the centroid of the distributed load.
So I guess as long as you keep track of your line of action, you can manipulate your free body diagram.
Right. And here's the short answer. I mean, that's why it is. But the short answer, like, if you're like, I don't want to understand it, I just want to know the rules. Because I think a lot of times those two things go together. They sort of reinforce each other or whatever. As long as your y-axis is up, as long as your y-axis is vertical, distributed loads and weight forces, the y component doesn't matter of where those are applied.
So it could be 0, right?
Yeah, you can set them to 0, set it to whatever, yep.
But the x have to...
The x is the one that matters, because the x position, you know, is not along that line of action.
Oh, okay.
So it's a line of action thing. Any other homework questions? Yep. 4? Anyone have that? Okay, so this one has a pin joint on the left side and it breaks up like this. This distance is 0.3 meters. This is 0.2 meters. There's a cable like this. This is 0.1. This is 0.1. This is 0.1. The pin is at the midpoint of, along that line of symmetry of that top rectangle. And then this distance is 0.4. I'm not going to go through this whole problem, but let me do the free body diagram. At the pin joint, you have a force vector. I'll call that RA. You have to calculate the centroid, and at the centroid there's a weight force of the thing has a mass of 200 kilograms, so this is 1962. And then the only other force is that cable force, T. You can use the locations of the two endpoints of the cable to come up with the unit vector for that cable, for that tension force. So in order to do this, rigid body problem, you're probably going to choose your about point here, So you might as well put your origin there too. And if your origin's going to be there, then that's where you want the origin to be for your centroid calculation. It doesn't have to be, but you're going to have to change things around after you find the centroid if you don't do it that way. So for the centroid, you can break this up a couple ways. This is the way I think I would probably do it, 1 and 2, with the origin here. And then calculate the area and the centroid of 1 and 2, use the summation formula to find the total centroid. And then all you need is the x location of the centroid because you're just using it for the weight, but you could calculate both of them. Yep.
So in this scenario, you would use the same origin for a centroid and a free body diagram because the line of action, if the line of action was horizontal, we could use different origins, but because the line of action doesn't line up with our original origin.
Like, why are we choosing this as the origin?
Yeah, like, because you said it's easier to use the same origin. Because in some ways it's easier to use different origins with the centroid and free body diagram.
Okay, so yeah, what if you chose your origin to be here? That's fine. You'll get a value for the centroid that's negative in x, positive in y. And then you have to decide whether you're going to do all your calculations for the rigid body problem in this coordinate system or whether you want to translate the coordinates that you got in this coordinate system into a new coordinate system. And then at that point you would think like, oh, I wish I'd just done it this way from the start,
Is it safe to say you could just choose the best origin to a free body diagram and just make that your centroid origin?
Yes, that's, I think, what you should always do, yeah. Okay, so let me stop questions there, but I have office hours on Wednesday, so if you have any questions, I'd be happy to talk about it there. Whose was this? Okay, so today we're going to introduce structures. And this is the main topic in this class. If you went to 100 professors, engineering professors, and asked them to test you on how well you know statics, 97 of them would say they don't have time to do that, and that's a weird question to ask. And the other 3 would give you structures problems. Okay? So this is like, how well do you know statics? If people want to know how well you know statics, they want to know how well you know how to do structures. And structures are, a structure is a collection of rigid bodies connected by joints. And the way we're going to go about it, the idea is kind of simple. We're going to isolate each individual body, and we're going to write out Newton's laws for each rigid body. And in the end, we're going to have a lot of variables and a lot of equations from Newton's laws, and we're going to solve a big system of equations. And depending how many bodies you have, it doesn't take very long to get up to 15 or 20 equations.
So will these be the same type of joints we've seen before?
Yep, the same. So in a way, this is nothing but a bunch of individual rigid body problems where at the end you just have to solve a big system of equations. So we're going to isolate individual rigid bodies. And find Newton's laws. After that's been done for each body, you have a big system of equations. And the way you want to solve it is reduced row echelon form. You're definitely not going to look at this and think like doing it by substitution looks fun. So I am going to start by I'm going to introduce a problem. We're just going to think our way through it, and there's nothing that we can't just think through with the knowledge we have now. But after I think through it, and I think what I usually do here, I'm going to do this problem 2 ways. And then after I do that, I'm going to give you a general set of steps that will sort of streamline the process. Okay? So the first thing I'm going to do is just think through a problem. So there's no real process yet. So let's say that we have an equilateral triangle. Each of these is 1 meter long. And let's say there's a force of 500 newtons applied to the right from the top pin. In order to keep track of what member we're talking about, let's think of the left member as number 1, the right member as number 2, and then if I want to refer to the pins, I'll think of this one as A, B, and C. And let's say that we want to calculate the external loads on each member. Okay, so one thing we could do is we could think of, we could isolate member 1, member 2, and then those pins, you can think of those as sort of individual, you can think of those as individual things. So we could do a particle statics analysis of the pin A, pin B, and pin C. Let's actually skip that step. So what we're going to do instead is we're going to lump these pins in with bodies. You know, that's fine to do. They don't have to be connected or whatever. We're just going to say, we'll assume that we'll treat pin A as part of the ground. Pin B as part of member 1. And pin C as part of the ground. And that's going to cut out a few equations because we're not going to have to isolate those pins. Those pins, we're just treating them as part of the body. And now I'm going to start with member 1. We'll do a free body diagram of member 1 and just go through that analysis. Okay, so what loads are acting on member 1? Oh, and let's ignore the weight for now. Ignore the mass of this thing. Okay, so what forces are acting? Down here at pin A, that's a pin joint. So what type of loads are acting on member 1 at A? Full force vector, yep. Just using the rules of these joints.
We're just treating that as part of the ground load?
The pin is part of the ground, yeah. And so this is a force applied by the ground. It's really that pin to the member. And I'll just call that RA. That's a force vector applied by the ground. The same way you would if that was a rigid body problem. And then up at B, now all of the forces up here are being applied. They're not really being applied to member 1 proper. They're being applied to the pin. But we're treating the pin as if it's part of member 1. Okay? We're lumping it in. So what forces are being applied to member 1 up at B? Well, definitely that 500 Newton force. And second, there's a pin joint connecting 1 and 2. So there's a full force vector up here. We know it's a force vector because those are the loads that a pin joint applies. And I'll write this as the force on 1 by 2. Any questions about that free body diagram?
It's just for one, so only the one body, right? Because we have to
This is what you're always going to do is just isolate the individual bodies that make up the structure.
and this has three individual body, right?
It just has 2 in this case because we're not going to isolate the ground.
We cannot put them together and like isolate them as one body, or we have to do it.
You can, but that's not enough.
Okay.
So-
Give more equation, like useful.
Yeah.
We do it and
So we'll see how many variables we have, and we'll see that that's just not enough to do it. I mean, from this one alone, right now we have 1, 2, 3, 4 variables. We know we're only going to get 3 equations from a rigid body, so we know that this isn't enough to do it. Okay, so now let's figure out the forces and the moments. What do you want to choose as an about point for this? Yeah, so choose it up here. I don't know. It eliminates the moment for 2 forces instead of 1. So, so okay, for the force 1, 2, what's the row vector? F12 acts at the about point. So that row vector, if you think about this red dot as being the origin, the row vector is 0, 0. The force vector is F12x, F12y. Cross product is 0. And now we'll do that 500 Newton force. What's the row vector for that? 0. The force is 500, 0. Cross product is 0. And now the last one is this RA force. What's the row vector for that? We're looking for a vector that goes from there to there. So that's 1 times, this angle is 60 degrees. Oops. So that's 240. Yeah. So cosine and sine of 240. And you get negative 0.5, negative 0.866. the force is RAX, RAY. And the cross product is negative 0.5 RAY plus 0.866 RAX. Any questions about any of that? So now we're just going to write out these equations. The first equation, I'm just going to skip the step of writing out Newton's laws, but and I'm just going to put them into the equation form that we're going to use later. So Newton's second law, the x components say F12x plus 500 plus RAX is equal to 0. If you reformat that, it says F12x plus RAX is equal to negative 500. Anyone not like me doing this? Should I just write it out? Maybe it can't hurt. Okay. Everyone feel okay with this? Okay, and then the second equation says F12y plus RAY is equal to 0. And then the third equation says, I'm going to just rearrange these, but 0.866 RAX minus 0.5 RAY is equal to 0. So those are our first three equations. And let's think about what we have as variables. We have F12, that's a full vector of variables. And we have RA, that's a full vector of variables. So we have 4 total variables, the 2 components for each one. And we have 3 equations, so we know we can't solve this system. So we're just going to hang on to these equations and isolate the other body. So now a free body diagram of member 2. All right, so what forces are acting on member 2? Well, the easy one is at C. That's a pin joint with the ground. So I'll just call that RC. And now let's think about what's happening up at the top. This is a little trickier. Remember that the way we have it drawn, the way we've decided to think of this thing, member 1 is a combination of this rigid body 1 and the pin. So member 1 is a body with a pin in it. Okay? Member 2 doesn't have a pin in it because you only have one pin, right? And we chose to lump it in with member 1. You got me on that one? And so, so that 500 Newton force is applied to the pin. It's not applied to member 2. It's applied to member 1. And so it's not going to show up in our free body diagram of 2.
But 2 and 1 are stick together.
That's right, but 2 and 1 touch each other. So there is a force on 2 by 1.
Oh, on 2, okay.
Okay? So there's no... So over here there's a force on 2 by 1, but there's no 500. And, okay, so let's think for a second about what variables we're going to introduce with Newton's laws. We're going to introduce RCX and RCY. There's no way around that. So we're introducing 2 new variables for sure. But now let's think about this one. F21X and Y. We don't have those variables yet. But we do have F12X and Y. And Newton's third law says this is equal to negative F12. So if we use Newton's third law to re-represent F21 as negative F12, we can reduce the number of variables that we have. Yep.
But isn't that F21 representing all the force coming from member 1?
Yes.
Wouldn't that include some amount of force from the 500 Newton force?
That 500 Newton force does, if you took that away, there would be a different reaction force up here. So you're right about that. But all of that, whatever that 500 Newton force does, it's applied through this force F21. It translates to this force F21. That 500 Newton force can't be applied to member 2 because it's not acting on 2. Just the same way, we've thought about that with rigid body statics before. If a force isn't acting on the boundary of the body you're looking at, then you don't put it in the free body diagram.
Okay. Because what I was thinking is F12 is just specifically the pin, but F21 is meant to represent any force that comes from member 1, which to me it would seem like that 500 Newton force would have some kind of impact on it.
It has an impact on it, and that'll come through in the equations. So you're right about that. If you change that 500 Newton force, this calculation we're doing is going to change the value of that F12. You're right about that. But you don't need to put it in separately. Its influence is already coming into the equations through the force it applies to member 1. Okay, so rho F MA. And what do you want to choose as an about point here? It doesn't really matter. They both have the same number of unknowns, same number of total forces. Let's put the about point at C. So we'll think of that as the origin when we calculate these row vectors. Okay, so first, the force RC. What's its row vector? 0. The force is RCX, RCY. Cross product says 0. Now, what's the row vector for F21? That's negative 0.5, positive 0.866. That's just cosine and sine of 120 degrees. The length is 1, so 1 times the cosine and sine of 120 degrees. The force vector, we don't want to use the F21. We want to use the one we've already used. So I'll call this negative F12x and negative F12y. And so the cross product is 0.5 F12y plus 0.866 F12x. And that's all the forces. So now I'm going to just add to our list of equations. Our fourth equation is Newton's second law for the x components. So RCX minus F12x is equal to 0. Our fifth equation says RCY minus F12y is equal to 0. And our sixth equation says, I'll just reorder those, 0.866 F12x plus 0.5 F12y is equal to 0. Okay, so now we're up to 6 equations. Let's think about our variables. We have F12, x and y components, RA, x and y components, from those first three equations, and RC from the second set of three equations. So 6 variables. 6 equations, 6 variables. That's a system we can solve. Okay, so once you solve that system, what you get out of it is I wrote this sort of funny. F12 is negative 250, positive 433. RA is negative 250, negative 433, and RC is negative 250, positive 433. Okay, so now let's think about what that tells us about the forces acting on those members. So let's go back to a free body diagram of 1. Down at A, we have negative 250, negative 433. Up at the pin at B, we have negative 250, positive 433, and we also have a 500 Newton force to the right. All I'm doing now is filling in the variables that we had from the free body diagram at the beginning. I'm just filling in the variables from the first time we visited this. I can rewrite this since this 500 Newton force is acting at the same point as this F12. This comes out to add up to positive 250, 433. And down here, negative 250, negative 433. Do you happen to notice anything about the directions of those forces? This isn't so important right now, but they're equal and opposite, and they are equal and opposite, and they also lie right along the line of this beam. So this beam is in pure tension, and if you calculate the magnitude of this force, it's 500 that way, 500 that way.
Wouldn't that just be zero net force then?
If all you want is, well, in statics, everything comes out to be zero net force, you know, because it's static. But this tells us important things about how likely it is that there's going to be a fracture somewhere. You know, if you apply a tension like this to the body, then it's going to behave a lot differently than if you apply a tension of 10,000 to it, you know. and then the free body diagram of body 2. Down at the bottom, we have RC. That's negative 250, positive 433. And up at the top, we have negative F12. So the opposite of this F12 that we solved for. So 250, negative 433. It's equal and opposite again. And again, it's lying right along the length of that body. This time it's the other direction, though. So this time we have a compression of 500, 500. So before I say something about the tension and compression that we have there, anybody have any questions about the process? There were some places where, you know, without any more information, I'm sure it would have been tricky, or you would have gotten stuck trying to make these jumps around using Newton's third law or whatever. But I think everything should make sense that we did, you know. Jesse, yeah?
As far as like numbering pins,
Yep.
if you were to have like a problem with more pins, do you typically, like, is a good way to do that, making the pins that are like on top like 1 and then pins that are on the bottom like 2 and so forth, so on and so forth?
You know, it doesn't matter, and that's an important point actually. This is a sort of a funny, cool thing about this. Like, what if I had numbered it the other way, and then I lumped the pin in with member 1 just because it's number 1, it should get the pin, you know. But what if we had called this member 1, and then the pin would have been over here, and then the 500 would have been applied to member 2? That changes everything, right? You'd think so, but when you get down to the end, you would get this exact thing back. So it just doesn't matter. The numbering that you choose is just for your own bookkeeping. This is the real thing, and no matter how you number it, this is what you get at the end.
What if the 500 were applied to both 1 and 2? Would that change the way?
Well, then it would be like if mathematically you applied it to 1 and 2, what that would be, you'd be solving a problem where instead of 500, this was 1,000, because you'd be double counting it, and so your answers would be wrong. Yep.
The numbers wouldn't be mirrored in any
Uh,
with the orientation or mirror the orientation, it would come out.
The numbers would be different, but then when you plug those numbers back into the free body diagram, they would be the same again. So yeah, you will get different numbers along the way, but in the end, when you give that final interpretation, it's the same. Yep. Yes?
Why can you use different coordinate systems when dealing with different numbers? Is it just because you're coming out with force vectors?
Well, what you're really doing is, in a way, you're not. That's a good and important question. You're not really choosing to change the coordinate system. What you're doing is just, that's an approach that you can use to calculate those row vectors. And those row vectors only care about, that's just a vector going from one to the other one. If you wanted to, and I think in my solutions this is still how it appears, you could keep the origin the same, calculate the coordinates of the beginning and end point for that row vector, and then subtract them to get the row vector, and you'll get the same answers as you do this way. It's just an approach to calculating row.
Okay.
Okay, so here, trippy. Why are the forces straight along the members, you know. That has to be the case for any two-force body in static equilibrium. So let's see why that is. So imagine that our two-force body is this. Okay, there's no reason it has to be straight. And let's say that the forces are here. I'll call that F1. And here, F2. Okay, so let's think about two possibilities. Okay, well, what if they're not equal and opposite? What if one goes this way and one goes this way? Well, then it can't be in static equilibrium because the net force is not a zero vector, so you're going to get acceleration, translational acceleration. So that's not possible. These forces must be equal and opposite. Or there's acceleration, and that violates the, the whole idea is that this has to be in static equilibrium. And now how about this possibility? Okay, well, what if they're equal and opposite, but that doesn't explain why they have to be along the length of the member. Okay, well, now what if one goes this way and one goes this way? Those are equal and opposite, so they, what?
What problems are not equal forces?
Even if they are, they can be equal forces.
Oh, okay.
So let's say let's say that they both they're both r and they're equal and opposite. So now there's no translational acceleration. But what is going to happen with this? It's going to spin, and so those forces must be along the line connecting the forces. Or you'd get angular acceleration. That we're not going to do that very often. Like two-force members are not going to come up in structures very often, and that's because in a structure, a single member always has two joints to be a part of the structure, and if you, in addition to those, include the body's weight, that's a third force, and then this doesn't hold. So two-force bodies must be weightless. And that's why that's not going to come up too often, but I will talk about that a little more. That's part of the trust simplification that I'll get into later. Okay, so now let me give a general method for structures. And it basically just outlines the steps that we followed in the last one, but it's something you can sit next to you while you work through structures, especially at first, to make sure you're not missing any steps. Yes?
So for structures, will we generally just look at the individual pieces and not say two rigid body structures connected together?
Two rigid body structures connected together, you could still just solve it as a single structure, and you could use the same approach. You know,
Will it generally just be these like two force, one on each end members?
well, usually they'll have weight attached too, but there's no reason that they only have to have two joints on each member. I guess that will be the more common thing, but you could have 3 or more joints on a single member.
Okay.
Okay, so the first step. Number the members. At each joint, some subset of the members will join. All right, so let's say that this is the structure. You can number it however you want, but I usually do it from left to right. And if you think of a side view of, and these are all supposed to have be connected by pin joints. If you think of a side view of that top pin, you'd see member 1 and member 2 not touching each other, but each one touching a pin. And that doesn't actually have to be the exact way that the pin joint works, but that's a way to think about it, to understand how to do these calculations. So if this is member 1, this is member 2, this is the pin joining them. So members 1 and 2 don't touch each other, but each one touches the pin.
This scenario is at
1 and 3. Dang it! 1 and 2, that would be the other joint, but that's, okay, that's good you told me that, because that would have been very confusing. Thank you. Any questions about that? Second, at each joint, you're going to treat the pin as part of the lowest numbered member at that joint. The lowest numbered member touching that pin. Three for each member. You're going to use Newton's second law and rotational equation. And you're going to use Newton's third law to minimize variables. So for example, F12, or let's say what we did in the last example, F21 is equal to negative F12. And then the last one, the last step is to use reduced row echelon form to solve. Let me say one thing about step 2, treating the pin as part of the lowest numbered member. Okay, so here's that side view of the joint again. Let me just do this and then.
Yeah.
So here's the side view of that joint. We're going to assume that that pin is part of member 1. Well, we're going to lump them together. And so we're going to treat it like there's no, like member 1 and the pin are no different. And so member 3 now is touching the pin, but that pin is part of member 1. So in the picture above, 1 and 3 aren't really touching each other. Now 1 and 3 are touching each other. And if you have another external force there, it's going to be applied to the pin, which is part of member 1. Question?
Yeah, and so that's only applied if there's a force